Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. Christian Huygens, in his treatise on light, begins by advocating a philosophy of science wherein every natural event should be accounted for in terms of the motion of material objects. This is a very different philosophy than the one that had been adopted by the ancients, the medievals, and the scholastic thinkers. This is described at the bottom of page 160 in A Student's Guide to the Great Physics texts, and this is where I ended on my last lecture. He says, "And as, according to this philosophy, one holds as certain that the sensation of sight is excited only by the impression of some movement of a kind of matter which acts on the nerves at the back of our eyes, there is here yet one reason more for believing that light consists in a movement of the matter which exists between us and the luminous body." So again, the idea that he's advocating here is that our perception of sight, our sensation of sight, he says, can be accounted for wholly by the vibrations of some material that lies between the source of light and our eyes. He'll be developing this thought more in the coming pages, but remember what he's doing here is he's rejecting, on the one hand, the ancient and medieval view that immaterial causes, such as formal causes, efficient causes, final causes, can account for, are necessary to account for events and things in nature. He says only material causes are needed, so he's rejecting that on the one hand. On the other hand, he's also rejecting the philosophy of Isaac Newton. We're going to come back to this later and study a little bit more about Isaac Newton, but you might recall in my previous lecture I mentioned how Newton had a view of light where light consists of particles, material particles, that fly from the source of light to your eye, and that is why you detect light. So you might imagine striking a torch or a flashlight in the modern times, and when you turn it on, there's a stream of particles like a fire hose, if you want to think about it that way, flying from the light that then hit your eye. That too is a materialistic kind of explanation of light. Huygens has a materialistic explanation of light, but it's going to be a little bit different than Newton's. He's going to claim that there is some medium that fills all of space. And when you light a torch or light a flashlight, it causes vibrations of this medium that travel a bit like a sound wave from the source of light. They vibrate, these waves travel through this medium and cause the retina of your eye to vibrate, and that's how you perceive light. So we'll come back more to that later, okay? Now, what reasons does Huygens provide for believing this theory of light? This is at the top of page 161. He says, and this is the first reason he gives on account of the speed of light. He says, when one considers the extreme speed with which light spreads on every side, and how when it comes from different regions, even from those directly opposite, the rays traverse one another without hindrance, one may well understand that when we see a luminous object, it cannot be by any transport of matter coming to us from the object, in the way in which a shot or an arrow traverses the air. For assuredly that would too greatly impugn these two properties of light, especially the second of them. It is then in some other way that light spreads, and that which can lead us to comprehend it is a knowledge which we have of the spreading of sound in air. So what is he saying in this paragraph? He's saying, let's write this down. Let's say the evidence for Huygens' theory of light. He's going to provide evidence for it in the coming pages, but here he's providing negative evidence or evidence against the other theories. So the first piece of evidence against other theories, so maybe I'll just specify that, evidence for Huygens' theory of light or against competing theories such as Newton's theory, Newton's particle theory. First of all is the extreme speed of light. He's going to talk about this in the next couple of paragraphs, so we'll come back to this first one. But the second reason he gives is that light rays pass through one another. I forget exactly how he says it, but light rays pass through one another without hindrance. Okay, you might remember we talked about this in my previous lecture, where I said that if you imagine you've got a couple of flashlights that are each shining a beam toward each other, okay, and if you turn on these flashlights, the light comes out of this one, the light comes out of this one, and this one is able to illuminate the person holding this flashlight. So call this flashlight A, flashlight B. The light from flashlight A can pass through the light coming from B, and it can illuminate the person holding flashlight B. And likewise, the light from flashlight B can pass through the light coming from flashlight A and illuminate the person holding flashlight A. So how is it that light can travel through other beams of light without hindrance? He says, if you believe Newton's theory of light, or he implies here that if you believe Newton's theory of light, then you should not, it doesn't provide an explanation of how light beams can travel through one another, because after all, if they were made of material particles, then they would bounce off of each other, at least to some extent they would, okay? So they can't go from A to B like a shot arrow or like a particle. So think about an arrow going from here to there. He's saying that is not the way that it works, like a particle or an arrow flying from one to the other. He says here at the end of this paragraph that it's more like how sound spreads. So let me remind you of how sound spreads. The idea is that if you have some, let's just say a plate right here, and it's attached to some shaft, and this shaft can drive that plate back and forth, vibrate it very rapidly, what's going to happen is all the air particles that fill the region of space in front of it, you're going to have some regions where the air particles are compressed. So this is kind of when they're close together. As this thing vibrates back and forth, you have compressions and then expansions, and then a compression right here, and then an expanded region of air, and then a compressed region of air, and an expanded region of air. So if we were to plot the density on this axis, the density of the air versus the position, you here have a high density. Let me do this in orange so it's easier to see. A high density, low density, high density, low density, high density, low density. So that's what's happening with these air molecules, and then these waves travel in this direction through the air, and that is how sound works. So he is going to draw on the analogy of sound to explain how light works. So looking ahead, he's going to say that these flashlights, in a sense, are vibrating these small particles that fill the region between flashlight A and B. They're vibrating these particles, and the light is traveling as a wave from one to the other, and waves don't have the same kind of problems of bouncing off of each other that particles might. Okay, and then going back once again to the first issue right here, the extreme speed of light. He's going to spend the rest of the chapter talking about how the extreme speed of light suggests that light has to behave like a wave and not like a particle. So how do we know that light travels at an extreme speed? So let's ask that. How do we know that light travels at an extreme speed or an extremely high speed? Well, he talks about some recent experiments that were done. So he says, first of all, that at the bottom of page 161, he says, well, let's see whether or not the spreading of light takes time. He said, let's first consider whether there are any facts of experience which can convince us to the contrary. And there is where he begins by talking about an experiment that was done by Mr. Descartes. Okay, so recall once again, Descartes was a scientist and a philosopher around this time, a bit before Huygens, and a kind of a contemporary. I forget exactly when Descartes was born, but he's right around the same time, and he's the one who wrote a book that advocated that we at the very least we know that we exist because we think. That's the "I think, therefore I am" statement in one of his Meditations on First Philosophy, if I remember correctly. He also came up with the Cartesian coordinate system, which is named after Descartes. Anyhow, he came up with an idea of a way to measure the speed of light. And Descartes, I'll just jump right to the conclusion, Descartes believed that light traveled instantaneously. That is, it didn't take any time to get from one place to another. So this was the first answer. So I'll just say this, Descartes believed that light was instantaneous. And by that I mean it travels at infinite speed. When you turn on a light on one side of the room, you immediately see it at the exact same moment that it's turned on. It doesn't take any time to transit from the light bulb to your eye. Why did Descartes believe this? Well, he tried to come up with a way for measuring the speed of light, and that is described in figure 13.1. So let's look at figure 13.1. And what he depicts here is, you have to imagine it this way. He says, imagine you have, I'm going to put it in my own words. He says, you imagine you have the sun at point A. And let's suppose that the Earth is at point B. And that arc that goes from B to E to D, that arc represents the trajectory of the Earth as it's orbiting around the sun. And let's suppose that the moon, the Earth's moon, is at point C. And that circle, CGD, is going to be kind of at the orbit of the moon, or the anticipated orbit of the moon around the Earth when the Earth is at position B. Okay, so now what is he doing here? He's saying, let's suppose for the moment that light does take some time to travel from one place to the other. So like the light that's coming from the sun at A takes some time to get to Earth at point B. And then the Earth, of course, once the light passes the Earth, it takes some time to get over to where the moon is at point C. And let's suppose, he says, for the moment, let's just make up a number. Let's suppose it took 1 hour. So it's quite slow light. Let's suppose it took 1 hour for the light to get from the Earth over to the position of the moon when it's at position C. Well, what does that imply? It means that if the Earth is passing right between the sun at point A and the moon at point C, at that moment the Earth is going to obscure the light from the sun, and the moon would be in the shadow of the Earth. But when the Earth is kind of moving in front of the moon like that, it's going to take a little bit of time to have that, I guess, that shadow or the blockage of the light to travel from B to C. And that would be 1 hour long, he says, for example. And then for the that to bounce back to the Earth would take another hour. And as this light is traveling through space from B to C and C back to B, or rather the blockage of light is traveling in that direction, I guess the tail of the light that has been blocked, the Earth is presumably going to be moving around the sun. So let's suppose that in the time it takes the light to get to the moon and then back to the Earth has moved from B up to point E. Now, what does that imply? That implies that if you're standing on Earth and you wanted to see this lunar eclipse, you would look over at the sun when the Earth is at point E. You look over at the sun, it'd be at point A, and you look in the other direction over at the moon at point C, and those would not lie in a straight line because the light from the Earth took some time to get to the moon and back. And so at the moment of a lunar eclipse, the sun, the Earth, and the moon will not be lying in exactly a straight line. If the light was instantaneous, on the other hand, well then, if the Earth is at point B and it blocks the sun, at that very instant, the light would be blocked from the moon and you'd see it instantaneously, and so there would be a 180-degree angle between A, B, and C. So I guess angle A, B, C would be 180 degrees. They would lie in a straight line. The sun would be on one side of you, the moon would be on the other at the moment of the eclipse. But if the light, on the other hand, if the light takes an hour to get there and back, to the moon and back, then the Earth will have moved to point E, and the sun, the Earth, and the moon will not be in a straight line. Now, how big of an angle should this be? Well, he goes through some calculations. This is at the bottom of page 161 and at the top of page 162. He says if it took an hour for the light to get from the Earth to the moon and back, then that angle GEC should be about 33 degrees. So, and then of course the supplement of that angle would be angle AEC. Supplement of 33 degrees is 180 minus 33 would be what? 147 degrees, right? 147 degrees, that's right. Now, if on the other hand light traveled faster, then let's suppose that it only took, instead of 1 hour to get there and 1 hour to get back, let's say it took 1 minute to get there and 1 minute to get back. Well, then instead of 33 degrees as being the angle GEC, then it would be 33 minutes of a degree. So 33, a smaller fraction of a degree, but nonetheless, they wouldn't lie in a straight line. And so what Descartes proposes here is, let's look at the moon and the sun when there's an eclipse, and if they're not in a straight line, we should be able to detect that. And he says, well, when you do this, you actually cannot measure any deviation from 180 degrees of angle AEC. That is, they do seem like they're right in a straight line, which means that the light must travel so fast that we cannot detect the motion of the Earth during the time of the eclipse. We can't detect any variation of this angle. And so he said, to the best of our approximations, light seems to travel instantaneous. It's an instantaneous effect. It takes no time at all to travel to the moon and back. That is why Descartes believed that light was instantaneous. Now, of course, Huygens rejects this view. He says that I do believe that light travels at a finite speed, but he says it's very fast. And the reason why Descartes erroneously thought that light was instantaneous was because it traveled so fast that it's so close to 180 degree angle between the sun, the earth, and the moon that it's immeasurably small. But there was someone else who did a measurement not so far after Descartes, and this was a guy named Olaf Romer. And he spends a couple of pages talking about the experiments of Romer. And so let me just say a couple of things about this. This is related to figure 13.2. And basically what, I'll just tell you the end of the story first. He says that Romer was able, by observing the eclipses of one of the moons of Jupiter, to determine the speed of light. He measured the speed of light to be something like 2/3 the speed of light that we measure it to be now. Something like we now measure the speed of light to be about 300,000 kilometers per second, 3 times 10 to the 8th meters per second. Olaf Romer, if I remember the number in here correctly, measured it to be about 200,000 kilometers per second. He doesn't use the same units as we do, but that it ends up to be about the same thing, about 2/3 the speed of light that we know it. And that's extremely fast, but it's not immeasurably fast. And that is exactly what Romer was able to do. One of the difficulties in measuring it using Descartes' method is because the moon is so close to us that it hardly takes any time, at the enormous speeds light travels, it hardly takes any time for the light to get from the Earth to the moon and back. And so you cannot measure the motion of the Earth in such a small period of time. But if the light has to travel a much longer distance, there's something that you could be measuring the time of during that time interval. So what he did is he looked at the eclipses of Jupiter's moon. So now to the diagram, figure 13.2, imagine that the sun is at position A, as shown in the diagram, and suppose the Earth is going around the sun in this orbit going E, K, B, C, L, D, around in that direction. I think that's the direction he talks about in the text. And then let's suppose that you have Jupiter at point F. I know this diagram isn't to scale, but this is the idea. Jupiter is at location F, and Jupiter's moons are orbiting around Jupiter. And let's just pick out one of Jupiter's moons, and it's going around GHN in that direction. Okay. And as this moon of Jupiter passes behind Jupiter, it should pass through its shadow during position from G to H. Now we actually do observe eclipses of Jupiter's moons from the Earth. And so it's when the moon, one of Jupiter's moons, passes behind Jupiter, and we see it pass through Jupiter's shadow. Now, here's what we can do is we can count how many of those eclipses we see during a certain time period of the Earth. So if we measure 1 eclipse, 2 eclipses, 3 eclipses, 5 eclipses, 40 eclipses during a particular interval of time, we can simply count the number of eclipses. Now let's suppose that you count those eclipses during 2 different seasons of the Earth. So as the Earth moves from position D to position E around the sun, let's suppose you were to count the number of eclipses of one of Jupiter's moons that you see between point D and E. There's some frequency with which you see those. Now let's suppose you do another count of the number of eclipses of the same moon you see when the Earth is moving from B over to point C. That's the same interval of time, but the interesting thing is that you'll count a different number of eclipses during the time interval it takes the Earth to go from D to E than the number of eclipses you count in the time interval it takes the Earth to go from B to C. Why is that? Well, it's because as you're moving toward Jupiter, you're going to more frequently observe these eclipses. And as you're moving away from Jupiter on the other side of the sun, you see these eclipses happening less frequently because you're running away from the light, so to speak. So in region DE, as you're going toward Jupiter, you see these eclipses more frequently because you're moving toward the light that's coming from Jupiter. And on the other side, you see them less frequently because you're moving away from the light coming from Jupiter. This, by the way, is now known as the Doppler effect. And so by measuring the difference in the number of eclipses viewed in one region or one season compared to the other season, one can, using some mathematics, determine the speed of light. And Romer was able to do this. In one of the exercises at the end of the chapter, I explain this in a bit more detail. I allow you to go through the calculations if you like, but the idea here is fairly simple. The calculations aren't too bad, but he was able to measure the speed of light, and that is what he describes on page 164. And then, so why does Huygens care what the speed of light is? Well, he argues that light travels at an extraordinarily high speed. He says the velocity of light, I'm reading from the middle of page 164, he says that sound, as I have said above, travels 180 toises in the same time of 1 second. A toise is an older measurement of distance. The speed of sound is about 330 meters per second, so a toise must be something like, about 2 meters, about 6 feet tall or something. So 180 toises in 1 second. And the velocity of light, he says, is 600,000 times greater than that of sound. And why does he care about this? He says, well, the enormous speed of light is evidence against light being a projectile like something else. He says there's nothing else in the universe that can travel from point A to point B at the kind of speeds that would have to be attributed to it if there was actually a material particle going from point A to point B. But he says if you think of light as a wave motion can travel at enormous speeds. And so this is the very speed of light, the enormous speed of light, he thinks, is evidence for the wave theory of light.